Hi, so I'm going to be talking about the 2005 AP Calculus AB FRQ number 4. And what it says is, let f be a function that is continuous on the interval from 0 to 4. The function f is twice differentiable except at x equals 2. The function f and its derivatives have the properties indicated in this table. Part A asks us, from the interval from 0 to 4, find all the values of x at which f has a relative extremum. Determine whether f has a relative maximum or relative minimum at each of these values, and justify your answer. So from here we can see that since the first derivative indicates the slope of the function, and it changes from positive to negative when x equals 2, we can see that there's a relative maximum when x equals 2. If I were to draw this, it would look something like this, with a positive derivative going to a negative with a relative maximum right there when x equals 2. Part B asks us to sketch the graph of a function that has all the characteristics of f. So what I'll start by doing is looking at the x value in the corresponding f of x value. So when x equals 0, f of x equals negative 1. When x equals 1, f of x equals 0. When x equals 2, f of x equals 2. And when x equals 3, f of x equals 0. So those are the points that we know right now. And from there we can go into the derivative. And from 0 to 2, it is positive, meaning that the line will be sloping upwards. And then from 2 to 4, it is negative, so it'll be sloping downwards. And with the second derivative, we can see that since it changes from negative to positive when x equals 1, it goes from concave downwards to concave upwards because of the change of signs. Also, when x equals 2, it changes from concave upwards to concave downwards. Then, when x equals 3, it changes from concave downwards to concave upwards. So, what you'll end up with is a graph that looks something like this. And here's your graph. Part C states that we should let g be the function defined by g of x equals the integral of f of t from 1 to x on the open interval from 0 to 4. And on this interval, it wants us to find all the values of x where g has a relative maximum or minimum. So first off, what we need to do is get the derivative of g of x to find out where its relative extremum are. So to do this, we take the derivative of this, which is g prime of x. And then we also have to take the derivative of this side. And to do this, you plug x into the f of t equation, and you're left with f of x. We can see from up here that in the f of x equation, when x equals 1 and when x equals 3, f of x equals 0. Since this is the derivative of g of x, this means that these are the critical numbers for g of x. So with the critical points of 1 and 3, we can make a table to test the values of g prime of x. So when you plug any number from 0 to 1 into g prime of x, which equals f of x, we can see that it will be negative. And then from 1 to 3, we can see that f of x, which is g prime of x, will be positive. And from 3 to 4, we can see up here that g prime of x will be negative since f of x is negative. What this shows us is that g has a downward slope up until 1, where it changes to an upward slope, which is a relative minimum. Then it has an upward slope up until 3, to where it becomes a downward slope, which is a relative maximum. So from the work that we just showed, we can conclude that g has a relative minimum when x equals 1, because the derivative of g changes from negative to positive when x equals 1. And also we can conclude that g has a relative maximum when x equals 3, because the derivative of g changes from positive to negative when x equals 3. Part D asks us to find all the values of x from 0 to 4, where the graph of g from part C has a point of inflection. So, from part C, we know that the derivative of g of x is equal to f of x. And for the point of inflection, we need to find the second derivative. So the second derivative of g of x equals the derivative of f of x. Point of inflection occurs when the function changes concavity, and we can find this by finding out where the second derivative changes signs from either negative to positive or positive to negative. And we can see that since the second derivative of g of x equals the first derivative of f of x, and f of x changes signs when x equals 2, we can see that the point of inflection for the graph of g of x is when x equals 2. The final answer is that g has a point of inflection when x equals 2, because the second derivative of g changes sign when x equals 2.